So sorry for the delay, everyone, today. Let's get started. So what we're going to talk about today, last time we spent all class talking about dielectric materials, okay? And today we're going to talk about conductive materials. So as you know, when we're thinking about electric materials, there's insulators, which are dielectrics, and then there are conductors. So let's just touch on some of the main points that we covered yesterday when we were talking about dielectrics. So we started off with this idea of a dipole, right? So there's two ways that, there's two types of things that can happen. One is if you have a nonpolar dielectric. In a nonpolar dielectric, you just have these atoms, all right? And when those atoms are placed in an electric field, the nucleus displaces, and so you end up having a buildup of an alignment of positive charge towards the electric field, and then the electron cloud shifts in the opposite direction. It distorts, so you end up having a dipole that way. In the case of a polar molecule, the molecule already has some polarity associated with it. H2O, for example, oxygen is more electronegative than hydrogen, so you end up having a net negative charge on the oxygen side than the hydrogen side. So those things have a built-in polarity. And we basically said if you have a material that's composed of a bunch of these dielectric atoms or molecules, these dipoles will align to the field if you place a field across it. And as a result, you'll build up positive charge on the upper surface, or the surface where the electric field is pointing towards, and on the opposite surface you'll get a buildup of negative charge, and that's governed by this, it's just called rho s, the surface polarization charge. Okay, and then we talked about defining D and the dielectric constants. So we talked about how in a non-dielectric material, this del dot epsilon E is equal to rho V. This is Maxwell's equation. In a dielectric material, you get this epsilon 0 times E plus P, because you have a polarization effect. Okay, what defines a dielectric material is that you get this polarization effect that I just talked about. All right, so we talked about susceptibility. The polarization is linear polarization is proportional to the electric field. The more electric field you give, the more polarization you have. So P is equal to epsilon 0 times the susceptibility times E. The susceptibility is a material parameter. Different materials have different polarizabilities, and that's governed by the susceptibility. We usually don't use this susceptibility term. Instead, we use something called a relative dielectric constant. Epsilon sub R is equal to 1 plus the susceptibility. All right, and we use that because it gives us a nice compact equation which relates D to E. So D is equal to epsilon 0 times epsilon R times E. Epsilon 0 is a fixed constant, 8.85 times 10 to the negative 12 farads per meter. Epsilon R depends on the material that you're talking about. So epsilon R for vacuum is 1. Epsilon R for air is close to 1. For something like pure water, it's about 80. All right, because water is a very polar molecule. But we talked about in class last time, when you actually try to use water as a dielectric, it normally doesn't work because it's hard to get very, very pure water. All right, even if you have a few ions in there, that'll make the water conductive. It's no longer a dielectric. All right, the last thing we talked about was dielectric breakdown. All materials have this effect where if the electric field is strong enough, if we go back to the atomic picture, if the electric field gets strong enough, then electrons can actually be ripped away from the electron cloud. You're literally tearing the atom apart. And when that happens, that electron can actually shoot through the material. All right, so the material, if you have moving charge, that's current, right? Current means the material is suddenly conductive. So what happens in dielectric breakdown is that these atoms ionize due to the large electric field. There's these electrons shoot through the material, but it's also damaging to the material. So there's a spark, a very short amount, a large current for a very short amount of time, and it typically damages the material. And of course, the air is a dielectric material, and one example of dielectric breakdown is when you see lightning. Okay, so that's a very dramatic example of dielectric breakdown. All right, we talked about the dielectric strengths of different materials as well. Any questions from last time? Okay, so that's the quick recap. So in contrast, today we're going to talk about conductors. Okay, conductors are things like metals. Dielectrics were things like plastics, polymers, things that do not conduct electricity. So if I put a conductor in a static field, there are several possible things that can happen. And so I have like a flow chart to sort of outline what we're going to talk about today. The first thing that we're going to cover is a conductor in a static electric field when it is not connected to a circuit. Okay, you just have an electric field and you have a metal object in an electric field. All right, it's not connected to a circuit, so there's no current flow. What we're going to look at there is we're just going to look at the electric fields and the organization of charges. Excuse me. And the organization of charges in that case. And then we're going to move on to the second part where we say, okay, now the conductor is connected to a circuit. So, you have like a conductive wire and you connect it to a voltage source. So in this case, you're going to get current going through the wire. So in that case, we have to talk about not just electric field, but we also have to talk about current density. We have to talk about resistance, and we're going to get into power dissipation today if we have time. Otherwise, we'll cover that the next day. Okay. So essentially what we're getting at today is ultimately we're going to get into Ohm's law. Okay, we're going to actually think about Ohm's law from more of an electromagnetic standpoint, from fundamental principles. So some of these slides that are up here right now I added them recently, so I will post the updated slides later this week. All right, so first of all, conductors in a static field. What happens when we place a metal object in an electric field, but without current flow? Okay, so if we do that, the charges typically would arrange themselves on the surface in a way such that the electric field inside the conductor is zero. As a result of that, inside the conductor, the charge density is zero and the electric field is zero. So what happens is that there's a surface charge density that builds up instead. So let's talk about this sort of from first, from basic principles. Let's say we were to take a ball, okay, a metal ball, and we transfer some charge to it. Don't worry about how we transferred charge to it yet. Just think about, okay, we transferred some charge to it. How is that metal ball going to behave? So that's what we're getting at here. So one of the unique things that happens in a metal is that charges can move through the material. As we just saw a picture of what the dielectric material looks like. If you in a dielectric material, you put an electric field across it, and those dipoles just align. But there's no conduction of current. Conduction of current means charges moving from one part of the material to another. Charges moving through the material. In a dielectric material, charges can't move through the material. But in a conductor, they can. And one way to kind of think about this is, and I talk about this in my other in my 4570 class. Let's say we have like a material here, okay, and we put a voltage across it. We're going to be talking about we're going to be talking about this like multiple times. So, so what you can picture here is there's an electric field that develops that goes this way. The electric field points from high to low potential. I'm going to sit down today. All right, the electric field goes from high to low potential. In this material, what's something that's unique about a conductive material is that there are electrons, there are charge carriers, and there are empty states. So let's say you have an electron here like this. The material has a bunch of empty states like this. It has electrons and it also has empty states. We're talking about a metal here, okay? In a metal, there are electrons. In a semiconductor, the situation can be a little bit more complicated. I'll go over this in a little bit more detail in a second. But for right now, the main point I want to make here is that these electrons can hop from state to state. So it can hop like this. And these electrons can move through the material. Now, one of the mistakes I made here is that electrons move opposite the electric field. So if there's an electron here, it would hop this way. If there's a positive charge carrier, it would move in the same direction as the electric field. But the point is that in a metal, there are carriers, charge carriers, and there are also empty states, so they can kind of bounce around and move through the material. All right, so if we go back to this, we're not even talking about current yet. But the point that I wanted to make here was that these charges are free to move around, whereas in a dielectric material, they're not. Now, given that charges are free to move around, the charges should end up moving around to the lowest energy state. Does that make sense? The charges will move to the lowest energy state. And, that's a more fancy way of saying, like, if you have a bunch of positive charges on the surface, those charges repel each other, right? So what are those charges going to do?
Find the place that has the least amount of negative charges.
Well, these are all. Let's say we have this example here where we have a bunch of positive charges on a metal ball.
They'll spread out.
Exactly. Did you guys see this? Intuition is very important. Intuition here. If the charges can move, those charges are going to move as far away from each other as possible, right? So if these charges in the metal ball, let's say initially we somehow injected. This is not very easy to do, but let's say we injected a bunch of charges into the center of a metal ball. Those charges can move. So once we injected them, those charges would basically go as far away from each other as possible because like charges repel. Right? The fact that a metal is conductive, the fact that these charges can move, the fact that these charges can move through the material means that the charges will basically move away from each other. In a dielectric material, the charges can't move. So in a dielectric material, you can actually build up charges like this inside the material. But in a metal, what will ultimately happen is that these charges will move away from each other and they'll end up just building up on the surface. Coulomb's law is just repulsion. As a result of that, something interesting happens. Number one, you have rho s, you have a surface charge density. Rho v equals 0. There's no charges inside the material. All the charges are on the surface. So, first thing, you have a surface charge density. Second thing, you have rho v equals 0. And then the third thing, and this is very important, is that E equals 0. in the material. Inside here, so let's say I took a point here. This is surrounded by positive charge. If we applied Gauss's law in here and we actually drew, you guys have done problems like this in your homework. If you had a sphere with charge all around, the way you'd find the electric field is you'd use Gauss's law. You draw a sphere in the middle here, and basically you'd find that the electric field anywhere in that sphere is 0. All right, rather than mathematically saying it, like I just want to tell you that these charges actually move around the interface so that the electric field inside the metal is 0. What also means is that if the electric field is everywhere inside the metal is 0, that means there's no voltage difference between different parts of the metal. That makes sense, right? A metal is conductive. Like it's very hard to have like 100 volts here in a piece of metal and then right next to it have 0 volts, right? Metals are like highly conductive materials are considered equipotential, meaning like the voltage is the same everywhere. Yes?
Okay, since the charges are moving, does it mean to generate current?
Oh, good question. So in this case, let's say I was just taking a hypothetical example is if we were somehow able to inject charge in the middle of this metal ball, those charges would quickly move to the outside. When those charges are moving, yes, there will be a current, but that current will be very, very short-lived. This is a transient current. Let's not think of like the current in this. That's not what we're mainly interested in. We're just mainly interested in what happens at the end. Yes.
One question would be, so does distance, the size of the metal object affect the voltage or the charge?
Does the size of the metal object?
So the way I'm thinking of it is if I test the voltage on the surface of the metal, it's like say small like square. Okay. No, it's small like ball. Okay.
Yeah.
Test it. I get an output. Okay. If I increase that size, would it still be the same output? But the same.
Oh, we'll do an example. Actually, one of our problems will be something like that.
Okay.
Yeah, that's a good question. Okay. 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 So, two important implications. Excuse me. Inside the conductor, charge density is 0. E is equal to 0 inside the conductor. But on the surface, there's a surface charge density rho sub s. And this is the part I haven't mentioned yet. The electric field is perpendicular to the surface. Why is the electric field perpendicular to the surface? Can someone tell me?
Surface vectors.
What's that?
Surface vectors.
Surface vectors. You're close. I think you're probably thinking what I'm thinking.
At each point there's.
Because of positive points everywhere. So.
Exactly. Whenever you have a system of positive charges, the electric field lines point away from that positive charge, right? So when these positive charges build up on the surface like this, the field lines just point away from it. That's the first Maxwell equation. Electric field lines point away from positive charge and they point towards negative charge. All right, so as a result, the electric field is perpendicular to the surface of a metal. And this is a rule that applies to all metals. Okay, whatever the shape of the metal is, whatever type of metal you have, the electric field on the surface of a charged metal always is perpendicular to the surface. Here's one example of where this type of electrostatics plays a role. Yes?
Yeah, I have a question.
Sure.
My lecture shows you that whenever we have the density is 0, that means we don't have water.
Whenever you have density...
Density is 0, that means we don't have water. Is it true?
Whenever the density is 0?
Yeah, that means there is no water.
Oh, just a second. Well, whenever the density is 0, you have water?
No water.
No water.
Yeah.
I don't quite follow, like I don't understand the relation to water.
Yeah, that's why I'm asking this question, because you told me this in this morning. You told me we were talking about the capacity. You told me whenever we have that density zero, and there is no water in the components.
No water in the components.
Yeah. See the density is related to the water.
The density of charges?
Yes.
Oh.
Is it true?
Well, if water is typically conductive, so if you have no water, then you can have charge density. But if you have water, and water is a conductive material, then your rho v is your charge density in the water is going to be 0. I don't know if I helped explain or if I confuse you more. We can talk about that after class. How about that? The example of electrostatics and metals is a good example is the Van de Graaff generator. Now, the Van de Graaff generator is actually there's a lot of physics concepts that goes into it. But I'll explain the simple part of it first, and then we'll talk a little bit more about how it works. So I had originally made this slide in 2009, the first time I taught this class, and it was the 80th anniversary of the Van de Graaff generator. So I thought it'd be cool to put that into the class. You've seen this at science museums. You touch this big metal sphere, metal ball, and your hair stands up. It's because that metal sphere has built up a lot of positive charge. And when you touch it, those positive charges are transferred to you to the point where you have so much charge in your hair that your hair starts to stick up because it's attracted to other negatively charged objects around it. Or there's also, I should say, the repulsion of positive charges from each other. Actually, that's probably a better way to explain it. If you just like the metal ball, humans were also made of conductive material. We're mostly water. In fact, we're mostly salt water, right? So salt water is conductive. So if we put a bunch of charges on ourselves, what's going to happen? Those charges are going to move to the periphery, right? They're going to move to the tips of your fingers, the top of your head, the bottom of your feet, right? So when you have all those positive charges, they would cause repulsion from each other. So if your hair gets positively charged, those positive charges will repel each other, and your hair will turn into a big poof like this. All right. So the Van de Graaff generator is something that is able to put positive charges on a big metal ball. Yes. Sorry, it's a question. And how it works is kind of interesting, but it involves actually a lot of physics, including something called the triboelectric effect. So how it works is that you have this metal ball. This is the thing that you actually see. Some Van de Graaff generators have this wand too, but it's not always, the wand here is not always present. So this is the charge, this is the ball where all that charge builds up, so that's number one, a hollow sphere where the charge accumulates. Number two is a metal comb with sharp tips on it. This is where the static charge is transferred to the sphere. All right, so there's actually positive charges that build up on this pulley system, and those positive charges are delivered to the sphere. Now, how does that pulley system work? It's through something called the triboelectric effect, which is something that we're not going to go into great detail in this class. But charge is, some of you have dealt with this before. You know that charges preferentially will go from one material to another. If a material is higher on the triboelectric scale than another one, then the positive charge will tend to go to it. If it's lower on the triboelectric scale, the negative charges will tend to go to it. So if you have two materials of different triboelectricity that have two different positions on the triboelectric scale, you get charge transfer between the two materials. All right, so in this case, a pulley roller is made of acrylic glass, and that builds up positive charge, and the negative charge builds up on the rubber belt. So this is an acrylic glass pulley and a rubber belt here. So what happens is this pulley is also rotating in the clockwise direction. So the negative charges are being transferred to the this rubber belt. This rubber belt is transporting the negative charges down here. So you're getting a buildup of negative charge here. Similarly, go on the upside, there's positive charges being delivered up to this belt. All right, and those positive charges are ultimately what's being transferred to the surface of the metal sphere. Now, the bottom pulley, you have to have different pulleys of different materials. The top roller is made of acrylic glass, and the bottom roller is made of metal. So metal has a different is a different place in the triboelectric scale, and in this case, in the bottom roller, it builds up negative charge and transfers positive charge to the rubber belt. So the rubber belt is getting negative charge on the top roller, and the rubber belt is getting positive charge on the bottom roller. So these positive charges are being transferred up here. The negative charges are moving down here. So that's what ultimately is building up the positive charge on this plate. The negative charges can be transferred through a comb to the wand. And so you would get a similar negative charge buildup on this wand, and if you touch the two together, you can get a static discharge between the two, lightning basically. So that's how the Van de Graaff generator works, but for the purposes of this class, the thing I want you to mainly know is that these like charges repel each other, and so you get a positive charge buildup on the surface of the generator, and then when you go to touch your hand on it, the charges transfer to you, and the positive charges in your body like repel each other, and that's what causes your hair to go up. Any questions about how this thing works?
I've seen other Van de Graaff generators where it's like two holes and sparks just travel like up it between them, like to the top.
Oh, is that the Jacob's ladder thing? Yeah. I think we were talking about that last time in class. Yeah, we were talking about that Jacob's ladder thing last time in class. This is a kind of interesting phenomena. So yeah, there are different types of this, but the phenomena is basically that you can build a positive charge on one end and a negative charge on the other end using the triboelectric effect. So let's do a simple example here. What if we have a conducting sphere? Suppose we deposit a charge Q on a sphere with radius A. The first question is, what is rho S? And the second question is, what is the electric field at a radius R? And you could figure out the electric field at R is greater than A and R is less than A. For R is less than A, it should be pretty straightforward. For R is greater than A, you should derive a formula for it. So I'll give you a few minutes to try that on your own, and we'll go over it.
What's the formula for
The surface area of a sphere is 4 pi r squared.
Can't you use Gauss's law?
You can, in fact, use Gauss's law for the second part. The first part too, but the first part is pretty straightforward.
Could you show the equation for rho s again?
What's that?
Equation for rho s?
Rho s?
Yeah.
I mean, how do we solve for it?
No, I mean, what's the equation? Is there an equation for it?
No. There's no equation for rho, just to deliberately solve for rho s here. So you just have to utilize the knowledge that the charges distribute themselves equally on the surface. All right, I'll give you all another minute to see if you can figure this out, and then we'll go over it.
Are you gonna upload these slides on Blackboard?
I will, yeah. All right, any leads?
Second.
How about the first part? How do we figure out rho sub s?
Q divided by the surface area of or capital Q divided by the surface area of the sphere.
Correct.
You say.
Correct. So we have a sphere, and there's a total charge of Q deposited on that sphere, but that charge distributes itself equally on the surface. All right, so the surface charge density, rho sub s, is equal to the total charge divided by the surface area of the sphere. So it's equal to Q divided by 4 pi a squared. The radius of the sphere is given to you as a. All right, so next we're going to find the electric field. So we found the rho sub s. Now we're going to find the electric field. So with the electric field, let's first find the electric field for R is less than A. So what is the electric field for R is less than A? This is, yeah, that's correct. Electric field is equal to 0 because everywhere inside a conductor, the electric field is 0. For R is greater than A, how do we find the electric field?
Is it Gauss's law? Yeah.
Yes, Gauss's law is back. So I'm gonna see. We can use Gauss's law to find this. All right. So what we want to do is draw a Gaussian surface around this. And everywhere on that Gaussian surface, there's an electric field E sub R. We choose a spherical Gaussian surface in this case because the field everywhere is going to be parallel to the surface, and the field everywhere is going to be equal to each other. It's going to be uniform. Those are the criteria for the Gaussian surface. And since we've gone over a lot of problems in Gauss's law, so we're going over this one fairly quickly. Q over epsilon. Q is the total charge contained within the Gaussian volume, the Gaussian surface. Epsilon is the dielectric constant, is equal to the double integral of on the surface, a closed surface of E dot ds. Now, from your previous from the previous problems that you've done, you know that if the electric field is equal everywhere on the surface, if it's the same everywhere, then this just becomes E sub r times the surface area. E sub r times the surface area, which is 4 pi a, or 4 pi r squared, my bad. 4 pi r squared. That's our Q over epsilon. And then your E sub r, the electric field in the radial direction, is equal to Q over 4 pi epsilon r squared. So for r is greater than a, the electric field is equal to Q over 4 pi epsilon r squared. For r is less than a, it's just equal to 0. So any questions about how we solved that one? Feel free to ask if there's anything that you're not completely clear on.
So piece of S is always, piece of S is always Q divided by surface area.
Good question. So for this particular problem, since we're dealing with the metal, so the metal, in the metal, the charges will deposit themselves on the surface. And since you have a sphere, since it's symmetric, they're going to deposit themselves equally on the surface. They're going to be equally spread out on the surface. So if you have a total charge Q, then the charge density, the surface charge density, is going to be Q divided by the surface area of the sphere.
What if I had a metal piece of wire?
If you had a
metal piece of wire?
Like a cylindrical wire?
Yeah, same thing.
Yeah. Except now the charges would distribute themselves. The charges would be more the surface of a cylinder instead of the surface of a sphere.
So Q over whatever the 2 pi r h, whatever.
2 pi r h, right. Right. You got it.
So would you count the ends of the cylinder?
So, in that type of case where you have a really long wire, most of the charges are going to be on the surface, the cylindrical surface, and there's going to be very little charge in comparison on the top and bottom cap. So you can just effectively ignore the top and bottom cap. There will be some charge there too. Yeah, it's flickering. It's a Halloween thing, Did you hear that there's a legend that there's a professor who died in this building, and to this day he haunts this building?
His last name Basu?
I'm joking. I'm totally joking.
He does like all of stuff.
Especially on the old one car.
Oh, we're already past Halloween, so that joke is old now. Today's what?
Day of the Dead.
Today's the Day of the Dead?
Yeah.
I thought it was Devil's Night was the day before Halloween.
Say that it is Mexican.
The Day of the Dead is the day after. Oh. Which country is that celebrated?
It's South Mexico, and I'm sure South America as well.
Yeah.
Oh, interesting. Shall we go on to the next example? Next example is we have a spherical shell. Suppose we have a point charge in the middle of a spherical shell. So we have a shell like this, and we have a charge Q in the middle of that shell. The question is, how are the charges distributed on the inner and outer surface of the shell? So I'm going to draw the shell as an annulus around here. Ignore that straight line. I don't know why that showed up. So let's say this has a positive charge Q. So the question is, what type of charges will build up on the inner surface of the shell? What type of charges will build up on the outer surface, and why?
There'll be negative charges in the outer surface, positive in the second surface anyways.
You are correct in the sense that there will be opposite charges on either surface, but your polarities are mixed up.
So negative on the inner, positive on the outer.
You'll get negative on the you'll get negative on the inner, positive on the outer. Why is that, Noah?
Because all the negative charges in the like inside the shell be attracted towards the positive charge.
You got it.
Will be repelled.
You got it. Yep.
I think I was looking at the electric field going outwards.
So let's draw the positive charge here again, because PowerPoint is not good for drawing. So let's say we have a positive charge Q here, and then we have, the inner surface of the shell and the outer surface of the shell. Okay. So getting to your point, Jeremy.
Yeah, I was saying I thought because the electric field was going off the surface that the field usually goes from positive to negative and something negative on the outside. That's what I thought.
Oh, you're thinking positive.
Yeah.
Okay, so you're thinking that the positive charges. Well, if the electric field is going in the outside direction, then the positive charges should move in the direction of the electric field.
So are the positive charges on the outer shell?
No. The negative charges are on the inner. The negative charges are on the inner shell. Positive charges are on the outer surface of the shell.
Yeah. So what you're saying is correct.
And then you get positive charge buildup on the outer surface of the shell. All right, the reason why, at least the way that I'd like for you all to think about this, intuition is really important. In a metal, charges can move. So imagine that in the metal you happen to have like positive and negative charges. So some types of, I shouldn't say metal, but a conductive material, some types of conductive materials can have both positive and negative charges associated with it. If those charges can move, those negative charges would be attracted to the positive charge on the inside. So you'll get a negative charge buildup on the inside here. And since you're getting a negative charge buildup, you would also end up having a charge buildup of opposite polarity on the other side. Because the electric field is pointing in this direction.
What if you have a negative charge?
That's what I was thinking. That's what I was thinking at first. Okay.
There's another important part of that here too. Excuse me. Go ahead. Question.
What about if the electric field is going inside, going the opposite direction? No.
I'm sorry. Say that again.
Okay, you said that the negative are in the inner and the positive at the outer, because the electric field is going up from, for example, from the twin to the up to the positive. This going this direction. What about if the electric field is going?
The electric field is being generated by that point in the center. So long as you're looking at a sphere with positive charge in it, the electric field will point out. That's the only way it points. The field's being generated by that.
The way you should think of it is that point starts off, right? It's positive. So there's a negative around here, and because of that, it's being positive out here. And because it's positive on the outside, electric field is going outwards.
But the question was that how?
If it was negative on the inside, that would point the opposite.
Yeah.
Basically.
So this type of problem will actually depend a lot on like what type of charges are in the conductive material. Most conductive materials, like they have electrons, free electrons, and they don't have free holes. So why don't we get into that? Why don't we get into that discussion right now? Let me delete this. So let's talk about conduction. So now we're getting into another topic here. So we're now talking about the second part of the diagram here. This is where you have a conductor in a static electric field, but it's connected to a circuit, so current can flow. Can I help answer the question? Sure. If there's, we can continue the discussion. If there's a point that we're confused about, let's.
Yeah. Can you actually clarify that?
Yeah, sure.
So what if you had a negative charge on the inside? Could you do the exact same thing?
If you had a negative charge on the inside, so let's say you had negative Q here. In that case, you'd end up attracting. You'd end up attracting the positive charges. You'd end up attracting the positive charges on the inner surface here.
In what direction would the electric field point?
Yeah, the electric field would point towards the negative Q.
Okay, gotcha. Think that clarifies it?
Yeah.
Okay.
So I got it.
Good. No problem. All right. So we're going to go to the next, the right side of this graph now. So it's connected to a circuit now. So this brings us back to Ohm's law. We'll get there in a second, but this is where you basically connect a voltage source to a resistor and you get some kind of current, V equals IR. So this is back to circuits 1. But we're going to take more of an electromagnetic spin on this so we can look at more of the details of what is happening. So let's ask ourselves first, what is current? So electric current is the movement of charge through a conductive material. And as I was showing you earlier, it's the way you can think about it is you have like this material and these charges are hopping from one state to the next. So they're moving through the material. And so these charges are actually being injected by the circuit. So there's actually electrons going into the material, and these electrons are actually exiting the material on this side. All right, that flow of electrons is the current. And I say electrons because most of the time we're talking about metals, and electrons are the charge carriers in metals. If we're talking about semiconductors, there can be positive and negative charge carriers. I'll talk about that in a second. But electric current is essentially the movement of charge through a conductive material. So what differentiates conductors from dielectrics is that they can support electrical current, so they have a conductivity. And the units for current is coulombs per second. So as an example, let's say you have a wire and there are 5 amps of current passing through that circular cross section. That means there's 5 coulombs of charge passing through that cross section every second. All right. So like a coulomb is quite a bit of charge. We'll talk about that. Now, revisiting this again, V equals IR. This is something you've learned in your Electronics 1 courses. You apply a voltage to a material, and if that material is conductive, electric current will flow through there. Different materials have different resistivities, conductivities, whatever you want to call it. And the relationship between voltage and current is given by V equals IR. So when we're talking about Ohm's law, we're talking about a specific type of current called drift current. For those of you who have taken semiconductors, you know that there's a second type of current called diffusion current. We are not going to be talking about diffusion current in this class. Okay, so all the currents that we're talking about here is due to electric fields, is drift current. So the questions we want to answer right now is, what is drift current? How does it work? How does drift current flow through a semiconductor or a conductor? What determines the resistance of a material? I think the reason it says semiconductors here is because I was using some of these slides for my semiconductor class This is for all materials. Okay. The first topic we want to talk about is what current density is. So with current density, we want to imagine current flowing through a wire. All right, and that wire has some cross-section. So in the case of a circular wire, which we're accustomed to seeing, it has a circular cross-section. All right, and along the circular cross-section, you can imagine all these vectors. These vectors are the current density, and we denote that by J. At each point on the cross-section of the wire, there's a current density J, and the total current is found by adding up all the current density vectors in the cross-section. So we're adding up this arrow here, this arrow here, this arrow here, and so on. So when you're adding up a bunch of vectors, you know that that's basically a surface integral. So the formula here is the total current is equal to the integral of J dot ds. When you integrate, that means you're adding up. Integration means adding up. So J dot ds. So what is ds? ds is, so imagine you have a cross section here. So in this case, it's a circular cross section. The magnitude of ds is the differential area. So in the case of a cylindrical coordinate system, it would be r dr d phi. We'll do an example problem here. And the direction of it, ds always points perpendicular to that cross section. All right, so the cross section is this circle here. The ds vector points perpendicular to it. So in essence, it points, the ds vector in this case points in the same direction as the current density vectors. So we'll see an example of that in a second. So basically, it is the integral of J on this cross section. So if J happens to be same everywhere on the surface, if J is uniform everywhere, then the current is just equal to I is equal to J times A, where A is the cross-sectional area of the wire. Units for J is amps per meter squared, and the units for I is amps. Right? This makes sense because if you think about current density, it's the current per unit area of the cross-section. Multiply that by the area, you get the total current. Any questions on current density? Let's do an example here. So this is a simple problem of uniform current density. Suppose the current density in the cross section of a wire is uniform. J is equal to 0.1 amps per millimeter squared. The wire has a radius 5 millimeters. What is the total current? All right, so we'll do this one fairly quickly so that we can move on to the next one. The current is going to be equal to J times A, right? Because we have uniform current density means we can use this formula here. I is equal to J times A. So the J that we're given is 0.1 amps per millimeter squared. And the radius is 5 millimeters. So the area is going to be equal to pi r squared. So it's pi times 5 millimeters. Don't know why it does that. Pi times 5 millimeters squared. Be careful about the units when you're doing these types of problems. This is actually a nice, easy example. So you end up getting millimeters squared in these units here, and you have 1 over millimeter squared here, so the units cancel out nicely. So you get 25 times 0.1, so it's 2.5 times pi amps is the total current. All right, so this is a very simple problem. Another example here is non-uniform current density. Suppose we have a wire with non-uniform current density. Suppose the wire is on the z-axis and the current density is given by J of R is equal to 5 times R. What's the total current in the wire? So this is the type of problem where you have, so imagine you're on the z-axis here. All right, the current is going in this direction. So this is the z-axis. The current is going in this direction. The current density is given by J of R is equal to 5R. What's the total current in the wire? So this is an example where you have to use I is equal to the integral of J dot ds. So I'd like you to just see if you can figure out what ds is, what J is, and see if you can do the integral and figure out the total current. So I'll give you a minute to try that. So when you're approaching these problems, remember, write down what ds is. It's a vector quantity. Write down what J is. It's a vector quantity. And then figure out your limits of integration, and then figure out the current. Oh, I should also mention the radius of the wire is A. So just to, assume that it has a radius of A. So, okay. How are we going to go about solving this problem then? Let's start by, let me just redraw it here. Like I said, PowerPoint drawing is not great on there. So here's our wire with radius A. All right. Total current I, let's say I is going in this direction. I is equal to, keep in mind I is a scalar quantity, is the integral of J dot ds. So whenever you're dealing with these dot products, it's good to write down the directions of the vectors as well as the limits of the integral. So J is equal to 5R, and what's the direction of J? It's in the z hat direction, right? Correct. And let's also write down ds. Okay, what's the magnitude of ds? So ds is going to be, one of the little patches of area on the cross section of the wire. So the magnitude is going to be r dr d phi, and the direction? Z hat. Right. Right. Again, this is imagine a small patch on the cross section. Oh boy. That's clumsy. There we go. Imagine a small patch here on the area, and the ds vector, of course, points perpendicular to that surface. So it points in the z hat direction. And then you have r dr d phi is that differential area. All right, so we have 5r times z hat dotted with r dr d phi times z hat. And we have our integral. So what are going to be our limits of integration? Let's first simplify this a little bit. So this simplifies to 5r, because z hat and z hat, they're both in the same direction. So this then just becomes 5r squared dr d phi. All right, so we have a dr and we have a d phi. So those are going to be the two variables that we need to integrate. What's going to be the limits of integration for r? 0 to a. R is equal to 0 to a. And what's going to be our limit of integration for phi? 0 to 2 pi. Good. All right, because this is not a none of this is a function of phi, we can separate out these two integrals. So you end up with something like this: phi is equal to 0 to 2 pi d phi, and then the integral here, r equals 0 to a 5r squared dr. So this just comes out to 2 pi here, and this comes out to 5 over 3 r cubed, evaluated from 0 to a. And so you end up with 2 pi times 5 over 3 a cubed. Yeah, let me know if I make a mathematical mistake here. 10 pi over 3 a cubed. So that is the total current. So sometimes you can have a situation where you might have non-uniform current densities in the wire. For example, if it's a semiconductor wire and some part of the wire is more heavily doped than the other parts, then you're going to get more current density flowing through some parts of the wire.
This is an amps too?
I'm sorry?
Unit is amps.
It's in amps, yes. Thank you for that. We should put the units here. Amps. All right, so that's the total current in the wire. Now let's get more into the nitty-gritties and talk about what is electrical conduction. All right, as I mentioned before, it's the movement of charges in the wire. And those charges, the moving charges, create a current density. Current is moving charge. Now, in this example here, you can see there's actually two types of charge carriers shown. A negative charge carrier, which is the circle shown in black, and also the red charge carriers, which are positive charge carriers. Now, it turns out in a semiconducting material, you can have electrons and holes. So there's two possible charge carriers you have to worry about, or you have to think about. Let's deal with the single charge carrier first, right, because I think that's easiest to understand. So for this beginning part of this discussion, just ignore these red charges. Assume that we only have a single type of charge carrier. All right, so drift current refers to the movement of charge due to an electric field. So you can imagine, electric field means whenever you have an electric field, negative charges move opposite the electric field. Positive charges move in the same direction as the electric field, right? So if you put a stronger electric field on there, the charges are going to move at a faster velocity, and you're going to end up getting more current. So current means moving charge. Right? That sounds very simplistic. Current means moving charge. But what that means is like higher current. If you want to get higher current, you either have to get those charges moving faster or you have to have more charges. Right? So let's look at some of these equations and what they mean. The current density is a product of charge density and velocity. U is the velocity at which the carriers move. All right, and we usually denote this U in bold letters to denote that it's a vector quantity. The velocity at which the electrons move is equal to negative mu times E. Now, don't confuse this mu with the U. It can be confusing sometimes because these things look similar. Mu is something called the mobility, and E is the electric field. Notice that the E is in bold. It's a vector quantity. Mu is a property of the material. High mobility materials are very conductive materials. In contrast, low mobility materials are not as conductive. Mobility, you can think about it, is a material property that describes how fast the charges can move through the material. We talk about this in my Electronics 2 class, but mobility actually has to do with the number of collisions. If you imagine a metal, right? If you imagine like there's a bunch of atoms there, and these electrons are moving through the metal. The electrons might collide into other electrons, they might collide into atoms, right? So the more collisions you have, the mobility is going to be less. By contrast, there are certain types of materials like two-dimensional materials like graphene or other types of new electronic materials which have super high mobilities, which means there's less collision, so the electrons can move more easily through the material. All right, so this mobility is a property of the material that you're talking about. It's a proportionality constant with the electric field. So U is equal to negative mu times E. The reason the negative sign is there is because why?
Opposite direction.
Electrons move opposite the electric field. Right. All right. So we've established how fast the velocity, like meters per second, how fast these charges are moving. The current density is equal to the product of the charge density and the electron velocity. All right, this UE is actually the same as this U here. Let me just make sure.
So the more conducting, the highest mobility.
That's correct. So let me just add UE here.
So the current density is equal to
Rho V times UE. So charge density times the speed, the velocity. This should make a lot of sense actually. Current is moving charge. So the mathematical definition of current density is how many charges you have, that's rho V. That's a charge density, multiplied by how fast those charges are moving. The units for rho V would be coulombs per meter cubed, and the units for velocity is meters per second. You multiply the two together, you end up getting coulombs per second per meter squared. In fact, just to make sure we all get that, let me just put it out on the OneNote here. J, the current density is equal to rho V times rho V times U, the velocity. So this is the velocity, at which the charges are moving, so that's given in meters per second. All right, and this is the charge density. So when we talk about charge density, we're talking about how many charges are in the material per meter cubed. So it's coulombs per meter cubed. If we took a meter cubed chunk of that material, how many charge carriers would we find in there? Conductive materials have a lot of charge carriers. So if we multiply coulombs per meter cubed, multiply that by meters per second, we end up getting coulombs per meter squared per second. Now an amp is a coulomb per second, so we get amps per meter squared, and that's what current density is. Amps per cross-sectional area. All right, now this velocity we figured out earlier, so this, you can write down the rho v again here, but this u is equal to the mobility times the electric field. So it's mu e times e. Negative, thank you.
Is that u or mu?
This one is mu, and this one is u. I know it's a little bit confusing, maybe partly because my handwriting's bad, but I think u and mu is a bad idea that they have.
That J is equal to positive rho v times the velocity. It's supposed to be positive. Is equal to negative.
It should correspond with it. Oh, right. I'm sorry. Ignore this. The negative sign comes. The negative sign comes from the fact that u is equal to negative mu times the electric field. All right. So go by the slide here. Charge density times the velocity at which they're moving. So this UE is equal to mobility times the electric field. All right, and so this is where we define the conductivity of the material. Because we would like to have a simple linear relationship between the conductivity and the electric field. So we can define this thing here, this negative rho v times mu e, as a conductivity sigma. All right, so sigma is equal to negative rho v times mu e, and then the current density J is equal to sigma e. All right, the reason we've done this is now this sigma is a material property. The conductivity of a material depends on how many charges it has available and how fast those charges can move through the material. Metals are great conductors because they have a lot of charges available, and generally these charges can move fairly quickly through the material. What's a really good conductor that you know of? Graphene is an excellent conductor because it actually has very high mobility. Very high mobility. What's another example? Copper is a great one. Copper is used in a lot of the semiconductors nowadays. Silicon microprocessors, yeah, the metal layers, the metal layers that they put on top of there are actually made of copper. The interconnects are made of copper. Silicon itself is a good conductor when it's doped. Silicon on its own has a very low charge density, rho v. So it's going to have a low conductivity. But when you when you dope silicon with boron, it increases the charge density, so it becomes more conductive. So the sigma is a nice way to sort of encapsulate all the properties of the material into one constant. So we don't have to separately calculate we don't have to separately account for rho v and mu and the mobility. We just sort of lump both of them into the conductivity. Now, this is for metals. If you have a semiconductor, it's similar things apply, except you have two types of charge carriers instead of one. So now we think about these black circles and the red circles. The black circles move opposite the electric field. Those are the negative charge carriers, and the red circles move in the same direction as the electric field. Those are the positive charge carriers. In a semiconductor, the negative charge carriers are called electrons, same as metals. The positive charge carriers are called holes. Okay, and when you take 4570, you'll know what holes means. This is kind of the absence of an electron. But those holes can move through the material just like the electrons can. So when we have two charge carriers, the electron equation is the same as before. The electron velocity is equal to negative times mobility times negative 1 times mobility times the electric field. And in the case of the holes, it's just the mobility times the electric field. There's no negative sign here because the positive charge carriers move in the same direction as the electric field. When we find out the current density, we have to account for both types of carriers because both types of carriers can create current. So we have to do the linear sum of both of them. You have to add them up. So this term here, the first term here is the current due to the electrons, and the second term here is the current due to holes. Right, so it's just like, it's very similar to how we derived it for the metals, except we now account for two charge carriers.
If you doped it with P-type, when those go away, right?
Exactly, yeah, you remember. I'm glad you remember this from 4570. If your rho VE is much larger than rho VH, if you have a lot of electrons compared to holes, then this term starts to become insignificant. That's what happens in an N-type semiconductor. And in a P-type semiconductor, as Jeremy said, this term is actually much larger than this one. Rho VH is much larger than rho VE. And this term becomes the most significant. All right? But, so mathematically how we do this is now the sigma, we still have this relationship J is equal to sigma E, except in this formula, before with the metal, sigma was just equal to rho V times mu E. In the case of a semiconductor, the conductivity is now equal to rho VE mu E plus rho VH mu H. All right, so there's two terms we have to account for. All right, I'm going to jump ahead for just a second since Jeremy brought up this point. I want to mention it again. With metals, your conductivity is going to be equal to Q times mu N times N. Where Q is the charge density. So I'm using a different notation here. I'll change that before I upload it. Rho VE is what I'm calling Q here. I'm sorry, N is what I'm calling rho VE. For a general semiconductor, you have to count for the electrons and the holes, just like I showed you. For an N-type semiconductors, it's like a metal. You only account for the electrons, and for the P-type semiconductors, you only account for the holes. For the purposes of this class, we're mainly going to be dealing with metals here. We may have a couple examples with semiconductors, but not at this point. When we deal with Hall effect sensors, we might have a little bit of that. All right. So, I would like to do one problem here where we calculate drift current or current density. This is a tricky problem that I would like to try just so you know how to address these types of problems. So in this case, we have a free charge density of negative 0.3 nanocoulombs per millimeter cubed in a vacuum tube. Now assume that the current density is equal to negative A sub Z times 2.4 amps per millimeter squared. So I'd like you to find the total current passing through a hemispherical cap specified by R equals 5 millimeters. And secondly, find the velocity of the free charges. All right, so there's actually a lot in this problem. Actually, it might be, given that we only have 10 minutes left, it might be better to just leave this one for homework. Would you like to have this one as homework? Or would you like to just, would you like me to show you how to do this?
Would you be able to do this one for homework?
Huh?
Would you be able to do it for homework? Like, can we do it?
Oh yeah, you could do it as homework. I could give you some hints on how to do it, and I can give it to you as a homework problem. Okay. All right, how about we do it as a homework problem, but let me give you a hint. Yeah. The second one won't be too difficult for you to do. The first part is the tricky part. All right, I'm just going to draw this on here. So the geometry of the problem looks something like this. So X, Y, Z. So you have a hemispherical cap like this. Okay. And this, assume that this hemispherical cap has some radius. This radius is equal to 5 millimeters. All right, and I'm just gonna extend this line out. Now, this is the tricky part in this problem. All right, now, oh boy. You're asked to find the total current. I is the integral of J dot ds. Now, in the problem that we did earlier, J, this is a big hint I'm going to give you, J and ds were pointing in the same direction. In this problem, J and ds are not pointed in the same direction. Let me show you what I mean by that. The current density, so this is our J. J equals negative A sub Z times 2.4. So, let me erase this. So J is pointing in the negative Z hat direction. All right? So the current density vectors are going to be pointed this way. Now, what is ds? ds is a vector that is orthogonal to the surface you're integrating over, right? So ds is pointing this way. So that's the tricky part of this problem. Okay? So I would like you to use your geometry skills and use the skills that you learned from the last module where you're doing a lot of surface integrals and see if you can figure this one out. This is a three-dimensional object. It's a hemispherical cap in 3 dimensions. This one is best done in spherical coordinates. Yeah.
Is it the shell or is it like the whole thing filled in?
It's a shell. Yeah, it's an infinitesimally thin shell. It's a surface. It's a hemispherical surface, right? So. What we're doing in this problem is we're calculating the total current. That's the ghost of the. He's saying it's time to end class now.
Getting very excited.
Oh.
I think we should leave now.
Yeah, I'm actually getting a little spooked out by this. I have to bike home, so I have no, I have my helmet, nothing else. Okay, so I'd like you to try that as a homework problem. Now this one, we have like 7 minutes left. I would like to go over this one quickly because this is actually a very easy problem. This is conduction and a copper wire. So this is an example that's actually in the textbook. So we have a 2 millimeter copper wire with a conductivity 5.8 times 10 to the 7 Siemens per meter, mobility 0.0032 meters squared per volt second. A 20 millivolt per meter electric field is applied. Find the volume charge density, current density, the current flowing in the wire, the electron drift velocity, and the volume density of free electrons. So this question is asking you to solve a lot of different things, but it's actually a pretty straightforward calculation. All right, so let me just zoom in on the solution here. The first part is asking you to calculate the volume charge density. So these are all like just more or less plug and chug type equation. The volume charge density, what's a symbol for that? Rho, yeah, rho VE, the volume charge density. So that is this guy right here, rho V. All right, and so what you're given is you're given the conductivity and the mobility. So you have this equation that relates, the conductivity is basically equal to mu, the mobility times the charge density, right, from here. The conductivity is equal to the mobility times the charge density. So you're given what the conductivity is, you're given what the mobility is, and so you can then figure out what the charge density is. So that's essentially what you're doing here. Rho VE is equal to sigma divided by mu E, negative 1.81 times 10 to the 10 coulombs per meter cubed. Remember the units. For these types of problems, the calculation is very simple, but remember to have the correct units. Next part here. What is the current density? The current density is equal to sigma times E. All right, you're given sigma and you're given E. So again, plug and chug. Now, the thing I want you to remember in this part of the problem is that the electric field is given to you is 20 millivolts per meter. That means 20 times 10 to the negative 3 volts per meter. Right? When you do these calculations, it's best to do everything in MKS units. All right, so you can the units for sigma is given in Siemens per meter. That is an MKS unit. So you have your 5.8 times 10 to the 7, and then the electric field should be in volts per meter. So 20 times 10 to the negative 3 volts per meter, and your current density then comes out to amps per meter squared. 1.16 times 10 to the 6th amps per meter squared. Next question is what's the total current flowing through the wire? So whenever you have questions like that, you have to ask yourself, is this a problem where you have uniform current density or non-uniform current density? Because remember, we had different approaches depending on what which problem we had to solve. In the case of uniform current density, the current is just equal to the current density times the area. All right, so that's pretty straightforward. It's J times the area, which is pi r squared, and this is pi d squared over 4, same thing. It's 3.64 amps. The part D here is we figured out the current flowing through the wire. What is the electron drift velocity? Okay, so to figure out the electron drift velocity, it's equal to the mobility times the electric field. All right, so you're given the mobility, you're given the electric field. You see that they're moving at 6.4 times 10 to the negative 5 meters per second in this case. In the last problem, the volume density of free electronics. It should be volume density of free electrons.
Did you guys last semester?
Volume density of free electrons. So this is the one that I want to make sure that you all know how to do this because it's not just straightforward from the above equations. Volume density is the number of electrons per meter cubed. It's different than charge density. Charge density is coulombs per meter cubed. So it's the charges per meter cubed. Volume density is the number of electrons per meter cubed. So the units for volume density is just 1 over meter cubed. So in order to find the volume density, times times Q is equal to the charge density. Q, as you recall, if you remember, it's 1.6 times 10 to the negative 19. So let me write this down here. So N times E times Q is equal to rho sub V. All right, so you might want to just jot this down in your notes. So the units for rho sub V is coulombs per meter cubed. That's what we've seen before. This is 1.6 times 10 to the negative 19 coulombs. Q is a constant. You've seen it before. It's the charge for a single electron. So there's a negative sign there. Oh, we have a negative sign in the formula here. Sorry. Q is always positive. And the units for this is 1 over meter cubed. So if we multiply 1 over meter cubed times coulombs, we get coulombs per meter cubed. All right, so this is the volume density of electrons. Okay. And you do this calculation here and you find that there's 1.13 times 10 to the 29 electrons per meter cubed. That's a lot of electrons. This means, like, what this volume density means, if you were to cut out a 1 meter by 1 meter by 1 meter cubed of this material, you would expect to find 1.13 times 10 to the 29th electrons in there. Right? It's a density of electrons per meter cubed. All right, so that's a good stopping point. So right now we've basically covered what drift currents are, so hopefully you'll understand what those mean. And next we're going to start talking about Ohm's law, resistance and power dissipation in the next lecture. So have a good weekend. I don't expect that there's no homework right now, so this is your week off. Homework will start up again on Monday. You'll also Wednesday. You'll also have this COMSOL thing that you're going to be working on.
Are we meeting on Wednesday?
It's a good question. The Wednesday will be on your own. So we will not have a formal class on Wednesday. Instead, what I'm going to do is record a lecture on COMSOL, and then you can watch that lecture and then go to the lab and do the COMSOL thing on your own time.
Wednesday or?
You could do it Wednesday. You could do it Thursday. You could do it. And next Wednesday, 1 week from today, there's no class. That's correct.
And that project will be due on the next.
The following week. Yeah. Yep. Excuse me.
That was one question.
Yeah, sure.
That's about grad school.
Sure.
When you say there's